Welcome to this talk about optimizing server-side template injection payloads for jinja2. I'm Remi Gascou, also known as Podaleris, and I am at GreHack 2021. So in my work days, I work as an offensive security consultant, and I do mostly pen tests. And in my nights and my weekends, I work in vulnerability research, and I write open source tools on GitHub to exploit new vulnerabilities. On my website at podaleris.net, I also write articles about how to exploit new attack vectors and security concepts. In this talk, we are going to deep dive into template engines and more specifically the server-side template injection vulnerabilities that we can find in them. To do this, we are going to use the Python jinja2 module, which is very famous and very widely used. And we are going to create new payloads to exploit jinja2 SSTIs, which are shorter than the currently known payloads. So what is a template engine? Basically, a template engine is a new way of thinking how web application works, where the template and the data are clearly separated. If we take as an example older paradigms such as PHP, in PHP you would have PHP code and HTML code all mixed up in the same file. And of course, you can include files and you can do stuff in PHP to minimize this. But the main concept is that you have HTML code and PHP code living in the same file. And in template language, you would have only the HTML code and template code inside one file, but the data is actually in something else, like an object, a request, another file, a JSON file, or whatever you want. And the template engine will create the link between the two, where it takes as an input the template file with its template code, and it will replace inside the template file everything you want from the data. This template file is written in something called template code, which is kind of a programming language. It has for loops, it has while loops, and condition, variable name, comments, everything you want. And you can access the variables that you put in the data inside the template. So template engine replaces everything you need and everything you mention inside the template code and outputs your output string from the template, which can be an HTML page, markdown, it can be a string, it can be almost everything. What matters is only the template code inside the template. Everything which is not template code will not be interpreted by the template engine, therefore you can put everything you want. So these four modules are the most common template engines on Python, Mako, Genshi, Django, and Jinja. And in this talk, we are going to focus on jinja2 and more specifically jinja2 internals and how we can exploit how it works to create new server-side template injection payloads for jinja2. So this is how jinja2 looks like. As I mentioned before, jinja2 is a template engine that is written in Python and can render everything you want to a string from templates. And in Python, as you can see here in this screenshot, it's really simple to use. In 3 lines of Python, you can already create a template and render it with the data you want. In jinja2 template code, most variables are surrounded with 2 curly brackets, and it's really simple to use, as you can see here. That's why it's used in many Python modules and applications that are web applications that are based on Flask for APIs or simple applications, for example, or in templating such as Python docx to generate Microsoft Word documents, docx files from templates in Python. It's based on jinja2. So this is an example of an HTML template file for jinja2, where you have mostly HTML code and parts of template code that is used by jinja2 template engine. As you can see here, we have a for loop which iterates over the items in the navigation list to create HTML lists in the output file. And we have access to a variable called a variable. So this is really simple to use. So the server-side template injection vulnerability can happen when an attacker has control over the template file before being rendered by the template engine. This can happen in many ways. The most common way are when an attacker modifies the parameter of the request, which will be reflected inside the template before rendering. This is usually a result of bad code, like mixing format string and template engines can result in this kind of behaviors. And if the attacker has write access to the source template files, for example, using a file upload vulnerability on the web application, or by FTP with write access, or by any means, he can modify the template and inject evil template code to achieve remote code execution or to modify the template. So now that the attacker has control over the template file, we can consider the template engine as being compromised, because in most template languages, you have ways to execute commands on the underlying machine, either by exploiting the template engine itself or by using modules directly. So now that we have a server-side template injection vulnerability inside the jinja2 template engine, as an attacker, we would like to achieve remote code execution, meaning we would like to exploit the template engine to gain access to the underlying machine. In order to do this, we will need to access the OS module of Python, which gives access to shell commands. Uh, to do this inside the template language of jinja2, previous research have shown that you can use egg enter payloads, which are highly context dependent, meaning you have to find the offset of the module you want to import, in this case subprocess. Therefore, this type of payloads can be tricky to use. So the main question that we can ask is there other payloads in jinja2 templates? And more specifically, can we find context-free payloads which does not require any data inside the .render function? Also, can we find shorter payloads that can import the OS module? And this is what we will try to build. So inside jinja2 templates, you have something in the language code which allows to reuse code blocks. In this example, I create a block named title where I put the value, this is title, and I can reuse it in line 3 using self.title to access the previously created block. I just have to render the template, and here we have the line 6 and line 7 with the same string, which is the block title. So the template reference object in jinja2 will hold the values of the blocks that we previously created, and we can access them everywhere in the template from self.title, and we do not have to put on a variable called self inside the .render method on the template, because it's built in inside the template object and it's already linked to the template reference object. This seems really cool from an attacker point of view because it's context-free. We do not need anything in the .render function to access the template reference object. Therefore, we can use it as a starting point to create our payloads. So as we've seen, the template reference object in jinja2 can be accessed from within a template with the double curly brackets self. And it's a context-free variable, meaning you don't have to do anything in the .render function to have access to self. And it's always accessible. So we are going to use this as the base of our payloads. So as I mentioned earlier, if we want to achieve remote code execution, we will need to access the Python OS module. So we will need to find where we can access it from within jinja2, because inside the template code of jinja2, you cannot use classical Python syntax, and thus you cannot import modules traditionally. So we will need to find somewhere inside jinja2 where the OS module is already imported and how we can access it. So if we try to explore a bit of jinja2 using Python introspection, like the dir function, we can find by hand a path to the OS module from the root of the module. So jinja2.bccache.temfile.os access to the OS module. So this is possible to find one path to OS by hand, but it's clearly not possible to try every possibility of every path inside jinja2 by hand. So in order to find the path to the OS module inside the jinja2 module, we need to look at the Python object tree as a graph, and we are going to explore it like a traditional graph in breadth first search to list every possible path to our DOS module and to see if we can leverage one of these paths to connect to the template reference object that we found earlier. So as I mentioned earlier, Python offers introspection concepts, which means we can use Python internal functions to crawl the object's attributes and functions as graph nodes. And we are going to use a breadth first search because using this, we are going to find the shortest path to the OS module in first. And as we want to create the shortest payload possible, this is really useful. So here is a small animation that shows how we are going to work inside the Python object tree. So if we start at object 1, we are going to go in breadth first search. So up we access attribute 1 and attribute 2, then object 2, and the OS module, and we find a path to the OS module. And this path is at object1.attribute2.os. So when we explore the Python object tree as a graph in breadth first search, we can have at least two problems. The first one is cyclic traps, which means if we have, like in this example, an object which refers itself in one of its childs, you will have an infinite loop, meaning in this example, you will explore object 1, then attribute 2, then attribute 3, and you will find object 1 in the attribute 3 child nodes. So you will go loop to object 1, and you will start over. So this will create an infinite loop, and we need to avoid this. The second problem that we have is a long expression time, because during a breadth first search, we will encounter a lot of objects in the Python object tree, and we can encounter many of them more than once. For example, in this graph, we have object 2, which occurs 3 times, meaning if we explore object 1, we will go to attribute 1, then object 2, then attribute 2, then object 2, and we will have the object 2, which is referenced many times, but it's the same object. So we have a massive loss of time when exploring multiple times the same objects, and we will have the same result at each time because it's the same object. So we need to avoid this as well. So to solve both of these problems, I use the Python ID internal function, which allows to check the memory address of an object given parameter. So I just added a list called known IDs into my program, which stores every memory address of every object that has been explored inside the breadth first search. So when I explore child nodes of a node, I know every object that I already crawled, so I don't have to explore many times the same object. So here is an example of the output of my tool, which prints a found module with module name and the complete path from the source module to the target module that he found. It does not only looks for the OS module, and it lists every module it finds during the breadth first search. So in output of my tool, you also have a JSON file containing every path to the module that you want. For example, here in line 4, you have the module name, the target module name, for example, OS. And after this, you have a list of all the paths to OS from jinja2 with the complete path each time. So as I mentioned earlier, we are going to use the template reference object as a starting point because it's context-free, meaning it's always accessible from inside the template, no matter what you have inside the .render function. So it's really useful for an attacker. And we are going to try to connect the template reference object to one of the path to OS inside jinja2 that we found earlier. so that we have a context-free payload that can access OS each time. So in order to do this, we need to list all the attributes and methods of the template reference object. To do this, I used the dir function of Python to list every Python internal function and attributes. And as we can see here, there's only one attribute which is custom, which is not a Python internal function, and it's underscore template reference underscore underscore context. So we need to deep dive into this. So we are going to print the content of the template reference context variable to see what it has inside. And as we can see here in its string form, there is a lot of information that is printed out. But inside this information, there is three elements that stands out. It's the cycler, joiner, and namespace functions, which are classes declared inside jinja2.utils module, submodule. And it's really interesting because if we remember well what we had before, in the output of the path to modules from jinja2, we had a path to OS module, which is declared inside utils.py. This means that the OS module was imported globally in the utils.py file. And this is really cool because we could use cycler, joiner, or namespace classes to bounce and jump into the utils.py global variables and access the OS module, which is imported globally in this file. So we can now access the global variables of the utils.py file fairly easily because we can connect the self.template reference context to cycler, joiner, or namespace and use cycler, joiner, or namespace to jump into the utils.py globals using dot underscore underscore init dot underscore underscore globals to get out of the class and access the global variables of the utils.py file. In these global variables, as we can see, there is the OS module on the center of the screen. We now have a new payload to access the OS module directly from a jinja2 template, and this without requirements. This payload is shorter than the Agenter payload, and most notably, there is less special characters in it, so it will be simpler to use if there is filters in place. Also, as you can see, it's context-free, meaning it works even if the .render function is completely empty. And also, you don't have the offset problems that we had in the Agenter payloads, where there is an offset that you have to find each time you want to run the payload. In this payload, you don't have this problem. You can access the OS module directly and execute commands. As we can see here, I wrote a few lines of Python to try this locally in a jinja2 template. If we inject our payload with self-template reference context, cycler, joiner, namespace, one of these three, and access to init globals OS, you have access directly to the OS module from the jinja2 template each time, and the .render function is empty. So to finish this, we can add a little bit of optimization. As we see, we are already inside the template context because we are inside a template file which will be rendered by the template engine. So we are inside the template. Therefore, we can remove the self.template reference context from the payloads because the self.template reference context is an internal jinja2 object which we used to list the variables that are declared inside the template. But as we are already inside the template, we can use directly cycler, joiner, or namespace and access to init globals OS for each of these three directly. So we now have the shortest possible payloads to access the OS module from a jinja2 template. These three payloads are the shortest, are context-free, and more importantly, they cannot be fixed because they are using how jinja2 works internally. Internally, jinja2 uses the OS module inside the utils.py file, but if you cannot just remove the OS module from the utils.py file, and if a developer is using jinja2 in non-sandboxed mode, which is almost every application that I saw written using jinja2 was not using the sandboxing mode. So if someone does not use the sandboxing mode, it can be vulnerable to this because in sandboxing mode, there is no way to escape from the template. You cannot access to OS or to any other module other than the variables that you declared. But in classical mode, you can access the OS module with these three payloads, and therefore you can achieve remote code execution from a server-side template injection in jinja2. Thank you for listening. You can find my tools on GitHub, my news on Twitter, and my articles on my website. And I hope you enjoyed this.
Do you have any questions?
Yes, there are a couple of questions, at least from the people online at one point. First question from Python developers. It's pretty difficult to avoid to use OS module. It's absolutely necessary. And even when you include third-party code, what is the solution to protect against this?
The solution is not to use the OS module, but it's impossible. So it's not really a solution. I contacted jinja2 about this vulnerability, and in their point of view, it's not a vulnerability. And sometimes the idea behind that is, okay, we use the OS module, but if you can do what I did in the slides, like introspect into Python and escape from templates, the vulnerability is not in using the OS module, is before that. So in a way, it's complicated not to use it, but it's not the real problem here.
How about, do you know any exploits that would be using these issues against Django or Flask? And I think the reviewer was asking the question because she's using CTFD a lot, and CTFD is using Flask.
Yeah. Yeah, but the CTFD is really known. It's a CTF platform, and it's been really tested by many people, including inside the CTFs. So there is no known vulnerability in this. But the server-side template injection vulnerability always occurs when someone writes bad code, which mixes format string, string replace, and template engines. So in CTFD, it's really audited, so it should not have this kind of vulnerabilities, but it's not impossible.
Okay, thank you.
I don't understand. Not really, because you would have to modify the OS module, which is built into Python, so we cannot deactivate it, and we cannot prevent code execution from this. But inside the newer version of Python, you can restrict some functions. It's something called audit hooks, which can prevent part of this. You can use it to prevent code execution in certain ways. But it's not really, it's kind of new.
Okay, are there any other questions? No? Thank you, Remi.
Thank you.